and we do the review. No new material, just review. Hello and welcome back to Calculus 1, section 5.2 on definite integral. So, we would like to see if we can do better than approximating area under the curve. And the answer is yes, we can do better. And we can do better by sending the number of rectangles to infinity. So let's just take a look quickly at the graph. So say I have this function f of x, and I have these rectangles. If I use left rectangles, we get certain approximation. But then in blue, I cut each one of these intervals in half, and then I draw blue rectangles. You see how much better blue rectangles are, because this portion here and this portion here and this portion here used to be errors, but they are no longer error. So that's great. And then I can do even better than that, because I can let's do orange. I can cut those in half and then create rectangles. Now you've seen the picture earlier with a much better resolution done in the textbook. So when you make these, now they have less error still, which is great. So the more you cut, the better off your answer is, but you're getting more calculations. And this procedure carried out to infinity should kind of hint at least at the fact that you will get exact area if you have infinitely many rectangles. Because infinitely many rectangles means they're infinitely thin. And you can fit infinitely thin very densely to cover everything, right? Without any error. So now I know that my delta x, which is one of these, is given by b minus a over n, which is n is the number of rectangles, right? And I also know that each one of these rectangles, if I take a representative rectangle, is going to be f of x, and I'll put I because it's some rectangle somewhere, times delta x. So do we all agree that we get area of a single rectangle when I multiply height times the width, right? Now look what I'm going to do. I'm going to add all of the rectangles from 1 to n. So this formula now shortens. When you have like 4 rectangles, you go 1 to 4, right? If you have 8 rectangles, you go 1 to 8 on the summation. And you know that you are supposed, so if this one, I will erase this, but because I need the space. But if this was summation 1 to 4 of f of xi delta x, that is f of x1 delta x plus f of x2 delta x, right? 4 of them. So these counters here from 1 to 4 actually tell you how many rectangles you have. So I put n up there to say maybe we have 4, maybe we have 8, maybe we have 10, maybe we have 100, right? N allows you to have any amount of rectangles you want. And the link is right there with that I. that you will place the first time around. You place 1, the second time 2 and 3 and 4, and then you cut off whatever n ends. So what I have here is technically, this part is 5.1, because I have single rectangle calculated, and then I have whatever amount of rectangles that I want, 4 or 6 or 5 or whatever, 3. So that will be, so this much is 5.1. So what's new now in 5.2? I'm going to send the number of rectangles to infinity. That's what's new. So that piece, that limit in front, that it's sending number of rectangles to infinity, is going to make this area exact area. Just that limit. Because without the limit, we already said, without the limit, it's approximation, right? Because you will be using finite number of ends, 4 rectangles or 10 rectangles, right? And as soon as you have a finite amount of rectangles, you are immediately cutting the creating, I want to say, creating error. So this is equal to exact area. Now, the formula uses, it's not using xi, it's using ci as a letter c instead of f of x, f of c. So we have that the area is equal to the limit, n goes to infinity, summation I goes from 1 to n, f of ci delta x. So that is the official formula for area under the curve. The delta x is given as b minus a over n. Now, to just tie in another thing over here, b and a are, right, a and b are given to you. That's the interval on which you want to find the area. But the number n, right, number of rectangles, because n goes to infinity, you are dividing by infinity. So you see how the length of delta x is going to 0. And that's something that it's crucial for this to work, because the thinner the rectangles are, right, the less error there is. Well, if they're infinitely thin, then there is no error because they're infinitely thin. So find area for f of x equal x squared plus 1 on the interval 3 to 6. We will be able to calculate this exactly. The area that we get from this calculation will be exact. Now, in order for this to happen, by using the formula above, we have to set up the problem first. So, what do we have? Well, first let's draw, again, some random function. Doesn't have to be exactly x squared plus 1, it's just a random function. From 3 to 6. And then I just want to use representative rectangle over here. Call that delta x. So my delta x is 6 minus 3 over n equals to 3 over n. Note that number of rectangles is not given to you. And it cannot be given to you because we're going to send that n to infinity. So I can't say, okay, do this for n equals to 10, because as soon as I say n equals to 10, it's approximation and there is error. It's not exact. So we are leaving n as a variable because it's going to go to infinity in the last step of the problem. So we're going to leave it there. So delta x is 3 over n. The next order of business is to locate CIs. So what is CI, right, equal to? Well, the first one is A, the last one is B, and then you have all of these in between, partitions, right? The formula is A plus I delta x. Now, does this make sense? Well, hopefully it does. Let me draw x0, x1, x2, x3, x4, going on. The x0 is actually A, your first value. Now, do we all understand that there is delta x in between these guys? Are we all cool with that? There's delta x in between? So how do I get x3? How do I get x3? I start at A, whatever A starts, plus 3 times delta x. You see, 1, 2, 3 delta x's to reach x3. So the formula I have up there makes sense. To reach any location on x-axis, we can use A plus I times delta x, because you can reach locations with that. So I'm going to leave this as a side note over there. So now to develop my CI is simply A, which is 3, plus I times 3 over n. So I have the CI. Now when I look at my formula, I need f of CI. Okay. Well, my formula was x squared, so CI is 3 plus I times 3 over n squared plus 1. I'll just say from x squared plus 1, because that's what it is, right? I am plugging in CI. You see that in the formula it's f of CI. That's the input variable. So I plug that in, and then we move along. So now I compute this. 9 plus I 6 over n plus I squared 9 over n squared plus 1. I just expanded this and I used the formula. So a squared plus 2ab. Oh, 2ab. 3 times 3 is 9 times 2 is 18. See, that would be wrong. 3 times 3 is 9, times 2 is 18, in, and then we have I squared, n squared. Good. So f of CI is given as, and we can put the square first, so 9 over n squared I squared plus 18 over ni plus 10. Let me write this in blood. I is a counter. Meaning I equals 0, 1, 2, 3, not imaginary. Not imaginary number. When I learned calculus for the first time, you know, back in my days, Serbia, we use J, so we don't get into the issue of, oh, it's a complex number. But I is a counter. That's that I underneath the summation that takes values as, you know, 1, 2, 3, 4, and so on. Okay, I have all of the features that I need to write my, so I'll write the formula. Limit n goes to infinity. Summation I goes from 1 to n. F of CI delta x. I can plug everything in. Limit n goes to infinity, summation I goes from 1 to n. Instead of f of x, I have this mess. 9 over n squared I squared plus 18 over n I plus 10 times delta x was 3 over n. We have to take this limit. Woohoo, right? So this is where properties of sums and other things will play a major role. So the first order of business is to distribute 3 over n into each term. I should have told you to warm up your wrist because, you know, start a new page, start a new notebook for this problem. So multiply. We have 27 over n cubed I squared plus 3 times 18 would be 54 over n squared I plus 30 over n. Right, that's the when I multiply 3 over n in, distribute. And now summations are additions. So I can separate all of these into 3 separate sums. So this would be a limit, n goes to infinity, of summation 27 over n cubed I squared, I goes from 1 to n, plus another summation, I goes from 1 to n of 54 over n squared I, plus summation of 30 over n, again I goes from 1 to n. So this is the split. Split, and this was distribute. And now, in red, formulas from the book. These formulas say that summation of a constant is equal to Cn. Summation of I is n times n plus 1 over 2. Summation of I squared is n plus 1, 2n plus 1 over 6. And summation of I cubed is n squared over n plus 1 squared over 4. These formulas are in the book. So now, since the sum operates on i's as a variable, 27 over n cubed is a constant. You can kick it outside. So now I have limit, n goes to infinity, and now I kick 27 over n cubed outside to have summation of I squared. Right, goes from 1 to infinity, to n. Yeah. Plus kick 54 over n squared out, left with the summation of I goes from 1 to n of just I, plus kick 30 over n out to leave summation of 1. We're done. We have 27 over n cubed, and now I squared, you have n plus 1, 2n plus 1 over 6. Plus 54 over n squared, instead of I have n plus 1 over 2. Plus 30 over n times n. because constant, right? Constant, if it's 1, is just 1 times n, which is n. And now we need to take this limit. Goes to infinity. It all depends on how good with limits you are from, you know, these ends cancel at the end. If you remember our section on infinite limits, sorry, limits at infinity, 2.5 from 2.5 months ago, or 2 months ago, that limit said that you only care about the highest powers, right? The rest all go to 0. So technically 27 times 2 is 54 n cubed over 6n cubed. That's what you actually get. The rest is negligible, so we throw it away. Plus we have 54 n squared over 2n squared, and then we just have plus 30 because the other one canceled. So now n cubes cancel, and this one cancels, and all you're left with now is 54 divided by 6, that's 9, plus 54 divided by 2 is, very good, plus 30, for a total of 66. So it should be 66. A little bit rough around the edges, right? 2-page calculation, but it's an excellent conversation starter. Like if you are on the airplane or a train, you know, you can just randomly write one of these out. The person next to you exactly gets who always gets the armrest. Like sometimes I have 2 seats, right? We don't have to resort to unpleasantries. Let me show you some calculus and some physics. Run for my life. Great. Both sides. Sit in the middle, you know? Have both armrests. Or you can say, what's the integral of x squared plus 1 dx from 3 to 6?
Do I need a book for this one too?
And get 66. You know. Yeah, exactly. Because what's the integral of x squared? It's x cubed over 3 plus x. And now the new notation is you put this vertical line and say compute from 3 to 6. I'll give the formula when I'm done. So this is going to be 6 cubed over 3 plus 6 minus 3 cubed over 3 minus 3. Now 6 cubed would be 6 times 6 times 2 because 3 cancelled, and then plus 6 minus 9 minus 3. There we go. 6 times 6 is 36. 36 times 2 is 72. 72 plus 6 minus 12. 66. So now we can do it the same way when you go to the eye doctor. What's better? A or B?
What's 1 or 2?
Oh, 1 or 2. Well. definite integral says area under the curve is equal to the integral a to b, which are the limits for which you are in the numbers in between you are looking for the area, f of x dx. And it's computed by the antiderivative computed at b, antiderivative of x computed from a to b, which is computed as f of b minus f of a. This formula here bypasses the calculation above and makes it simple. So what this means is that the integral a to b f of x dx is actually the limit n goes to infinity, summation I goes from 1 to n, f of ci delta x. It's also known as a Riemann integral because the mathematician Riemann is the one who figured all this out. What do we do with this? We calculate areas, calculate energies, calculate a lot of stuff that is out there. Find area under the curve for f of x equals 3x cubed minus x squared plus 6 on 0 to 2. Right, so we are computing the integral 0 to 2, and in parentheses. Now you see why you need parentheses, right? Because delta x is the width. So dx delta x, we know that from differentials, the same thing. So just integrate each one of these separately, and then plug in 2, plug in 0. Let's see what we get. So what's the integral of 3x cubed? So 3 times x to the 4th over 4, yes. Minus, how about x squared? Cube over 3. And how about 6? 6x. We put a vertical line and say compute from 0 to 2. Now the formula that we just seen is compute at the upper limit first. So we have 3/4, 2 to the 4th, minus 1/3, 2 cubed, plus 6 times 2, minus everything computed at 0. So 3/4, 0 to the 4th, minus 1/3, 0 cubed, plus 6 times 0. Now the whole thing over here for 0 drops, so we don't have to worry about it, luckily. The rest we do have to worry about. 2 to the 4, that's 16. So we have 3/4 times 16, minus 8/3 plus 12. This cancels down to 12. So now this becomes 24 minus 8 over 3. Put over 1 times 3. 72 minus 8 over 3, which is 64/3. Exact area under the curve is 64/3. It's really straightforward to calculate this. If you know antiderivatives from 4.9, you will be able to obtain the second line. Now you're learning f of b minus f of a, the way to compute definite integrals. So if you know that, you are able to compute the third line. And then do the arithmetic to get the 64/3. So the formula says, if you're looking for the area under the curve, do the integration between a and b being the limits of integration, the numbers that you are given. And then find the integral, plug f of b minus f of a. So you do whatever you got up there, f, which is the antiderivative, compute the b first, and then subtract a. And that's it. But now you're looking at the clock and saying, well, there has to be more. Of course there has to be more. There's another 20 years of stuff after this, right? So it better be more in this lecture as well. And there is some cute properties and tricks that we can employ. Definite integral from a to a of f of x dx is 0. Why? You're not going anywhere, exactly. There's no width, right? What is the area between 3 and 3? What do you mean area between 3 and 3? You have area between 3 and 4. You don't have area between 3 and 3. Make sense? So clearly it's 0. So if you end up with same numbers, that's done. What happens if these guys are in the wrong order? Like this. You put b downstairs and the a up. Can you switch them? Yeah. You put the minus in front of the integral and you put ab f of x dx. So if they are in a wrong order, you put the larger number in the bottom and the smaller number up on top. We always go from smaller to larger number, right? But sometimes when you do some substitutions in chapter 5.5 and so on, you are going to end up with those things reversed, and then you have to flip them, which is when this rule kicks in. And the one that it's very useful, third property, you can break your calculation at any value. I'll have to explain this one more detail. So integral a to b of f of x dx is equal to integral a to c f of x dx plus integral c to b, that's a d, c to b f of x dx. Now, here's how this rule makes sense. If I have, and it's just a simple picture, if I have some function f of x and I want to compute area between a and b, sometimes we have to split. So you split, let's say here, at c. So now this becomes integral a to c, and this becomes integral c to b. You see that? And when you add them together, you get the whole thing. So integral from a to b, which is the one on the left, is equal to the sum of the two integrals on the right. And you can actually break into as many as you want. You can have 15 integrals over here, right? Just need to make sure that wherever you break, the next integral continues from that point. So a to c, and then immediately continuing c to b. So a to c takes care of this part, and then c to b takes care of that part. It's a very important rule. Very important rule. And we'll definitely see that rule in action. Let's do another problem, because we have time. What is the integral from 0 to 2 pi of sine x dx? What's the integral of sine x? Negative cosine. Nice. All right. So our antiderivative is negative cosine x, and then we have to compute from 0 to 2 pi. So I have negative cosine of 2 pi minus negative cosine of 0. Well, cosine of 2 pi is 1, so I have negative 1 minus, and cosine of 0 is also 1, so I have another negative 1. So I have negative 1 plus 1, which is 0. Right? Whew. If I draw a sine function from 0 to 2 pi, is there an area that I can color? Is there? Right? You see it. I can color. There's area that I can color. But look at the answer. The answer say area is 0. So do we see how that's wrong? Right? So what's the issue? The issue is that the sine function went under x-axis, creating negative area. which countered the positive area, and they subtracted to 0, and now it looks like, when you look at that calculation, that the area under the curve is 0, yet we know it's not because I was able to color. And this is where the rule that I just had up there comes in handy. What am I going to do? I'm going to say, okay, that didn't work. I'm going to take my integral 0 to 2 pi of sine x dx and break it into 0 to pi sine x dx plus integral pi to 2 pi sine x dx. And because this one is the one that goes under, I'm going to put absolute value on it to make it positive. If you run this calculation, you're going to get 4. And then you will see that the area under the sine function is 4, which is amazing because you have, first off, you have trig functions, like when do they have nice numbers, and then also your limits are 0 and 2 pi. Like, and now you've broken into like pi's and 2 pi's. And this is 4. It's really awesome, right? So now, when we compute this, in your lab 5 has this stuff on it, so you can practice this area going under the curve and making it negative and making sure. So now I have negative cosine x computed from 0 to pi plus absolute value of negative cosine x computed from pi to 2 pi. So negative cosine of pi minus negative cosine of 0 plus absolute value negative cosine of 2 pi minus negative cosine of pi. Absolute value. There we go. Cosine of pi is negative 1. So this is minus negative 1 minus another negative 1 plus absolute value of cosine of 2 pi, so it's negative 1 minus negative, and cosine of pi is negative 1. It's like 5,000 negative signs over here. So that's 1 plus 1 plus absolute value. Don't make the absolute value look like a 1. Minus 1. And then you have 3 negative signs, so minus 1. So this is 2 plus absolute value of negative 2. And then the total is 2 plus 2 is 4. So you see now, if you just go straight through for every problem without thinking, you might get the wrong area under the curve because a part of the graph dipped below x-axis and you didn't pay attention, didn't care, didn't know, whatever you pick, right, as a reason. So now you see that graphing and awareness of where the function is on the graph is extremely important, because you can't compute every problem precisely if you don't know that the graph is, strictly above x-axis or dips below or something like that. So it's important. It's important. One more example and we call it a day. We will finish chapter 5 next Saturday. Not next Saturday, so next Saturday is the review. The following Saturday, on the 1st, we will be done with the last 3 sections for the course. And then the following Saturday you pick to have exam, which is 8. After that exam, we'll have 3 hours of review for the final for the entire course. And then the 15th is the final. So it's a crunch time. One more problem from homework. they want you to compute. So make sure you distribute and then, you know, do all the proper things. 0 to 4, x minus 4 dx. I modified the problem, so it's 51 modified. It's not the exact question. So distribute, we have x squared minus 4x, in parentheses dx, don't forget that. We have our limits 0 to 4. Now we integrate, we get x cubed over 3 minus 4 times x squared over 2, computed from 0 to 4. Alright, this pen is becoming really annoying to use. So now I cancel 4 and 2 and get 2 over here. That's it. So now plug in 4. We have 4 cubed over 3 minus 2 times 4 squared minus 0 cubed over 3. So it's function computed at the upper limit minus function computed at the bottom limit. So that will be plus 0, 2 times 0 squared. I mean, these zeros go away anyway. Which is equal to 4 times, 4 cubed is 64. 64 over 3 minus 16 times 2 is 32. And those others are zeros. And we have a 64 over 3 minus 96 over 3 for negative 32 over 3 as the answer. So we have x squared minus the fourth, x cubed over 3 plus minus 2 over 3, okay. All right. We'll do more of this stuff next week. Bye.